In this video, we're going to find a power series representation of a function, and we're going to use differentiation for one of our steps. So we're being asked to find a power series representation for f of x equals x squared plus x over the quantity 1 minus x cubed. And then we're also asked to find the radius of convergence. Well, like most of these problems, we're going to start with our power series representation of 1 over 1 minus x, our geometric series. Notice that when I differentiate 1 over 1 minus x, I get 1 over 1 minus x quantity squared. So a power series representation for 1 over 1 minus x quantity squared will be the derivative of this power series, which will just be n times x to the n minus 1. And the series here will start at 1 because the first term over here is a constant. So we lose that first term when n equals 0. It just becomes 0. We need a 1 over 1 minus x cubed in the denominator. To get there through differentiation, we need to take another derivative here. So taking another derivative, the derivative of 1 over 1 minus x squared is 2 over 1 minus x cubed. The 2 is coming from the fact if I write this as a negative 2 power, we would have a negative 2, 1 minus x to the negative 3, and then we have a negative 1 on the outside from the chain rule, so the negatives will cancel. Here, we differentiated the left-hand side. We need to differentiate the right-hand side as well. Bring the n minus 1 down in front, decrease the power by 1, using power rule there. And again, here, the first term is a constant, so the n equal 1 term goes away, becomes a 0, so this series will start at 2. All right, so now we're ready to get a power series representation for the function that we're being asked to find one for. Let's first split it into two pieces and think about factoring out the x for both of them. That's where these x squared and x are coming in from the outside. It's making a 1 in the numerator in both of them. Notice that our power series representation that we came up with here has a 2 out in front, so we need to multiply by a 1/2 out in front to make the adjustment for the 2 that we need to get our power series representation. So that's why it's a divided by 2 here, because we have a 2 on top here. This is now just plugging in the power series. And then this is distributing the x squared into both of them. Or excuse me, the x squared into the first one, the x into the second one. We've pulled a 1/2 out of both of them out in front here. When we put the x squared inside of this one, it becomes x to the n. When we put the x inside of this one, it becomes x to the n minus 1. This one, now, we're just looking at what happens if we re-index this. Basically, we're looking for like terms, right? We want to try to add these two series together. So we're trying to get terms that are like each other. So to do that, I want this to be an x to the n instead of an x to the n minus 1. So I need to add 1 in here. If I add 1 here, I need to subtract 1 here. Okay, so if I re-index by subtracting 1, dropping from 2 to 1, I need to put n plus 1 in for n. I need to put n plus 1 in for n everywhere. So that gives me n plus 1 times n times x to the n. I can't quite combine the two series together yet because one starts at 1 and one starts at 2. So let's pop off the first term on this one, and then they both start at 2. The first term here is when you plug in 1 for n, you get 2 times 1 times x. So I get a 2x here. Both of these now start in the same spot. So now I can combine them by adding their terms together. Well, this would be n squared times x to the n, and then a minus nx to the n. This gives me n squared x to the n, and then a plus nx to the n. So minus nx to the n plus nx to the n will cancel each other out. So we just get a 2n squared x to the n. This one fits that same pattern if n is equal to 1, right? Because if notice I put in 1 here, I get 2x. So this series is the same thing. These two terms together is the same thing as starting from 1 to infinity of 2n squared x to the n, and all I've done is factor out the 2 in front, and now the 2's cancel, and we get sum from 1 to infinity of n squared x to the n. All right, all we have done in this entire process is differentiation and multiplying by a power of x. Differentiation doesn't change the radius of convergence at all. So that the original here that we started with had a radius of convergence of 1. So do these two, and hence all of these do. So everything here has a radius of convergence equal to 1.